I'm the Chief Technology Officer for Qnergy, and we've been active specifically in the natural gas space, probably for the last 7 to 8 years, more recently in the last 3 to 4 years, in eliminating methane and seeing what we can do in providing our technology specifically for doing methane mitigation within the natural gas industry. So we're all aware of the methane challenge. One of the things that makes methane more difficult than, let's say, other gases or other challenges is that it's extremely distributed. It's not only distributed across pretty much every different sector of our society and economy, it's distributed geographically. In many cases, the largest methane emissions in our country are remote by definition. And so accessing those and not just quantifying them, but resolving them is become an issue. And that's what we're here, and that's what we're all about. So this is a graph that you guys are well familiar with in this forum. But essentially it quantifies or attempts to quantify, and there's some discussion as to whether the leak rates are higher or lower, but it attempts to quantify the key sources of methane releases from within the natural gas industry. And in some of the cases, these leaks are fugitive leaks. They're unintentional, they're happening. We try to find them, quantify them, and fix them. In other cases, however, the leaks are intentional. They're part of the control process. They're part of doing business. We actually intentionally every day across the United States are releasing, hundreds of thousands of standard cubic feet intentionally of methane into the environment. And those are specifically what we're going to be addressing today in the talk today. But if we have some time, we'll talk about some of the fugitive releases as well. So a conventional system, really by nature of the fact that well pads are remote, and upstream natural gas well pads, by nature of them being distributed out across our nation, somewhat disconnected from our utility systems, had to figure out a way to power themselves. And it was a really efficient and effective means. If we go back 40 or 50 years, we'll just use the pneumatic power of the gas to power the well pad. And that's how we've built an industry. And this conventional system, however, is proving to be not only lossy from an energy perspective, it's becoming environmentally harmful and a concern. And so what we've done is come alongside these well pads and said, we're going to provide you a reliable, continuous utility connection, but without the utility pole. We're going to give you the power you need so as to be able to address those power needs, whether pneumatic or other, automation and others, so that you can run that same well pad just as effectively, just as reliably, but without having to deal with the methane emissions. Basically, our whole technology is based on our generators, which is it's a continuous run, base load, reliable generator, which was designed to run off raw methane, unrefined, directly out of the ground, will convert methane into electricity. Now, we can take a fraction of the methane that would have been normally released within the normal operation of a well pad, and we convert it into power, and we convert that power into pneumatic power. So we have additional devices that plug and play with our power generators, and they produce pneumatic power. So you have electrical power, pneumatic power, which then can provide a well pad a really seamless transition away from using methane as its pneumatic source of power to using compressed air. So basically, just in the broadest sense, that's what we're doing. And we'll dive a little bit deeper now, and we'll discuss how we actually go about it. So we take unrefined methane and we turn it into continuous reliable electricity in the small power range. Most well pads, funny enough, even though they're producing millions of BTUs an hour in many cases, and they power our industry, they themselves, the well pads, actually do not take too much power. A typical well pad is consuming roughly on order of 200 to 400 watts of electrical power. And then roughly, if you look at the pneumatic power that you need, depending on the size of the well pad, whether it's 2 wells or 4 wells or 6 or more, you're typically consuming, let's say, on order of maybe 400 to 500 watts per well. In pneumatic power. So if you have like 6 wells, that's maybe another 2 kilowatts and change and pneumatic power. So it's actually not a lot of power that these well pads need. Historically, getting reliable electricity, continuous electricity out to those well pads has been a challenge because at the small scale, a reliable source of electricity that doesn't really exist. Definitely not one that works off the raw, unrefined, untreated fuel coming out of the ground. So the Stirling engine, been around for a couple hundred years. It's not necessarily known for its energy density or its ability to accelerate, but it does a couple of things really, really well. And it was always born out of a need by some of our, not just Department of Energy, but also Department of Defense and the space industry, to provide continuous base load power for non-terrestrial applications. And there we stand alone among the stars. Literally, NASA declaring that we were the longest running heat engine technology in the history of civilization. It's really as a result of some work we did in the late 1990s, early 2000s, where we fielded a number of engines with NASA that have been running continuously now for 120,000 continuous hours. And if you do the math on that, you realize the magnitude of if you translated that into, let's say, an automobile engine or a diesel generator running for hundreds of thousands of hours continuously, it's something that just isn't really, it can't be done under the same umbrella or the auspice of that technology. So we have a really reliable technology that, funny enough, has a fringe benefit that it can run on pretty much any fuel that you can turn into heat, when we can then convert into electricity. Primarily our work within the space industry was with nuclear radioisotopes and other forms of heat generating energy sources. In the natural gas industry, we take what's available to us, which is the raw unrefined methane. We take that raw unrefined methane and I don't want to go into too much detail of how the engine works, just for the sake of time. I'd be happy to share with any one of you guys in more details. If you want, just reach out to me and I'll be happy to do so. But basically it takes an external form of heat. So as long as you can convert your fuel into heat, which we do using an extremely efficient combustion chamber, which I'll discuss briefly in another slide, we convert your methane or natural gas into heat. We can then convert that heat into expanding gas. Our engine is a hermetically sealed cylinder full of helium. Helium's an inert gas. As that heat gets impacted upon the helium expands. The expanding helium forces an internal piston, which we call the displacer piston, to move backwards. It then provides a pressure wave on the power piston, which then converts a linear movement into the movement of a magnet. And the magnet, through electromagnetic field, creates an electric voltage, and that electric voltage then produces power. Okay, so very briefly, you have a hermetically sealed vessel. If you heat it on one side, you can get gas expansion. If you cool it on another side, you can get gas compression. And that oscillating expansion and compression of gas force the movement of a piston, which then force the movement of a magnet, which then force power. Okay, really, really simple. You heat something up, you cool something down, and you get electricity. And as long as those two things are maintained, meaning as long as you can keep your combustion system converting some form of fuel, in this case methane, into heat, you can create a very, very stable and continuous supply of electricity. We use some really innovative proprietary power electronics to turn that electricity into usable outputs that are configurable as well as prioritized for customer uses on a well pad. For example, in a well pad architecture, not only is the customer interested in pneumatic power, of course, for their valves, but even more so would be, let's say, for safety events. You have a variety of safety circuits, such as ESDs and others on a well pad, that take even a higher level of significance or priority over maybe some of the normal operations of a well pad. So our electric generator is designed in such a way that we have decoupled outputs, and we can program those outputs so they can service the loads at a different priority level, so that the highest priority loads are always getting powered if there should ever be a conflict in who's getting fed power. Our generators are designed to work continuously, reliably for tens of thousands of hours. Very low levels of carbon monoxide and NOx. When I say low levels, we're talking 2 orders of magnitude lower than a comparable diesel generator. Between 1 to 2, depending on how you do the math, sometimes it's 1, it's 2, but we're talking a huge disproportionate reduction in NOx and carbon monoxides, and all of this off unrefined methane. We've done some tests with our combustion system compared to best in class of other technologies, so fuel cells, as well as thermoelectric generators, diesel engines that are internal combustion engines. And if you look here at the comparison, we're top of class when it comes to methane destruction. So we are turning those methane molecules into CO2. Like, in order to oxidize methane, you have to produce CO2 in order to get heat. That has to happen. But we do it very, very efficiently, to the point where one of our tests came out at 100%, the other one came in at 99.9999, simply because of the level of the sensor and its sensitivity. But in all practicalities, we essentially convert all CH4 into heat and CO2. And you can just see in comparison some of the other, for example, internal combustion engines are known to be quite lossy. They have what's called seal blow-bys or leak paths of methane. So an internal combustion engine working off natural gas, many of our backup generators spread out across the country, thankfully only work a couple hours a year. When they operate, they are leaking, 1, 2, 3% of their methane is leaking out of the seals of that internal combustion engine by nature of its operation. And so that's something that our continuous run generator does not have. So we can take our generator that converts methane into electricity, and we plug it into a redundant compressor package, which is designed to convert electrical power into pneumatic power. We do it with a number of features and elements that specifically meet the demands of the natural gas industry. We have redundant air compressors that are designed to complement each other. We provide notifications and alerts to customers regarding their airflow and regarding their air capacity at different times throughout the day, depending on the different pneumatic controls that you're using. And most importantly, we provide a suite of solutions. We have one well pads out there, and I believe our largest well pad we're serving today is a 20 well pad down in Texas. So pretty much anywhere between a 1 well pad and a 20 well pad, you have different air usages, and not one size fits all in this case. And so we have a variety of air compression packages which are designed to meet the different needs of those different well pads. So when you look at the cost of compliance, the real issue here is really the natural gas industry, from my experience, and we've been out in the field now for a good couple of years implementing these things. They want to mitigate their methane. I really can say that as honestly as I can. Sometimes we like to, I don't want to say demonize the natural gas industry, but in my experience, most of the well pad operators, if they know they have a leak, they want to address it. In some sense, there is financial gain, especially when natural gas prices are high, to preventing that leak. But the problem generally is it costs money to save money. And so they're always looking at, how do we save money? How do we save this methane leak in a way that doesn't break the bank? And so when you do the math of using a technology like ours, one of the benefits is it doesn't require any retrofits of any equipment on the site. They continue to use their pneumatic controls just as they use them. They don't need to upgrade or change any of their control systems, any of their network systems. Everything remains exactly the same. The only thing that they're doing is they're essentially turning the valve off for the methane, which is feeding the pneumatic valves, and they're displacing it with air. And so when you do the math on the cost of integration of an air package instead of methane package, we're talking very, very low levels. And this is prior to a fine or a regulation. When the regulation actually begins to fine these operations for their methane releases, it becomes actually a profitable, pretty much from day one, it becomes a profitable venture from a capital expense as well as from an operating expense. So you can just see the numbers here. We're talking about, in the single digits for doing methane mitigation without fines. The moment there's fines, it's we'll be saving anywhere between $20 to $30 in equivalency. by fine prevention. So there was the young lady in the beginning was talking about data and data analytics within methane. A huge part of what we do is data analytics, not just in terms of finding the leaks, which is a huge portion of what much of this forum has been recently concerned with, is how do we find the leaks and how do we quantify the leak. But we go so far afterwards is to begin to calibrate out operations as a function of what that data is telling us. And so all of our machines not only feed back power levels, but they also feed back air usage levels. So the user can not only see how much power his well pad's consuming, he can be able to begin to learn what different portions of his pad, if he has it segregated, are using at any given time of day, meaning what is the specific pneumatic usage. And so when a leak develops, he can then get ahead of it. The ability to not only control, but to also monitor real time provides a huge amount of power, and not power from an electrical perspective, but the ability to impact change upon that well pad is significant because of data. So for example, when deploying air compression package, we've seen, and this is not a doctored graph. This is real. We took it back from 2021. This is the actual date. The user shall remain anonymous, but they implement an air package, and within the first couple of hours, they see that their flow rates are somewhat north of 12 standard cubic feet per minute. Now, up until this point in time, this well pad has been active now for roughly 10 years. So for the last 10 years, this well pad has been emitting to the environment 12 standard cubic feet of methane per minute for years. Their calculations, however, showed that they should only be emitting something like on the order of 3. Okay, it goes back to that same graph. If we go back to the beginning, there's a huge disconnect between the actual reality, what's happening out on the well pad, versus what we've calculated should be happening. And we're seeing that in real life as we're implementing these packages. We're getting the aha moment as our customers are connecting up, actual measuring their actual leak rates. They're saying, wow, in some cases it's better. In most cases, it's been a lot worse. And so as we're able to not only monitor and measure and audit the amount of pneumatic power we're delivering to a pad, we're also able to go out and to fix the leaks. And so here you can see we let it run, we fixed a leak, and then another leak appeared, and we fixed that leak, and then finally we reached, it took about 3 days. Typically, what we're seeing is from implementation of an air package on a well pad, we see typically 2 to 3 days, 4 days of leak assessment, and then it kind of stabilizes out and runs at essentially what the calculated rate is what we all assumed that pad was working at for years, but never was. Now, what happens when all of a sudden something changes? So we have a tool within our database which can look back historically and say, for the last week, a certain well pad has consumed 2 standard cubic feet per minute, for example, averaged at minute intervals. And now all of a sudden, in the last 5 minutes, I've seen a spike. I'm now consuming double the pneumatic power. That can be communicated back out to a user. Not that 4 standard cubic feet per minute in itself is alarming, right? Because many pads are running at even higher rates. It's the fact that you've seen a certain pad that our data has taught itself should be working at a certain level, now working at a very different level. And it goes in both ways. If a normal healthy pad should be consuming 2 standard cubic feet per minute of air, and all of a sudden drops to a 0.5 standard cubic feet per minute of air, maybe one of your wells have shut in. Maybe one of your valves are now plugged, right? You're not consuming the air that you thought you should be. And so we can provide a bunch of diagnostics to operators based off machine learning is a big word. I don't intend, this is not really a full meaning of machine learning, but we do learn the behavior based off history, and then we can predict a future behavior, which when that future behavior is not met, we can flag on it and provide the user that input. And so those are the kind of interesting things that we can do with data. Another thing that's been interesting, that once customers have been able to address all their leaks and their pads begin to operate effectively, let's say, according to the calculations that a vent should vent to, we're finding that the initial estimations are actually lower than initially assumed, because there's a certain level of buffer that many of these operators were putting upon themselves and saying, well, all the vents together should be at 2 or 3. I'm going to assume I'm actually running at 6, or I want to run at 9. Give me a package that can do 9 standard cubic feet per minute, even though my vents should only be consuming 3, because I need a buffer, because I know I need leaks, because I know I need to have the capacity to address leaks. And so if you take our top 10 customers, and this data here represents hundreds of sites, hundreds, not 1, 2, and 3. We're talking hundreds and hundreds and hundreds of sites. You can see that the average usage for a typical 4 to 6 well, 4 to 6 wells per pad is roughly about 2 standard cubic feet per minute, which really, from going back to the numbers, really makes sense. It took time to get there, right? It doesn't happen overnight. It takes a couple of days, and they need to assess and fix and resolve the different issues. But from a long-term perspective, it's not a huge amount of air. 2 standard cubic feet of air at 100 pounds is not an undertaking, which from a technical perspective, to create that is not a huge undertaking. It only takes a couple kilowatts. We can provide redundancy, and we can provide stability as well as reliability. And that has been really comforting as that data has been coming back, because when we first launched back in 2019, 2020 with our air packages, which, by the way, was interesting, we came from the industry. It was actually our customers that use our remote power package, meaning existing customers that were powering their electrical portion of their pads with our generators, said, could you design an air package for us that would provide us redundancy, provide us these solutions so that we could do our pneumatic power as well? Actually, the first time one of our customers asked us, we turned them down. We said, we're just really an electrical company. But it made more and more sense that we need to be able to provide customers with that solution. But we were scared that we wouldn't have enough air, because the estimations in some of these reports, and Evan has been in this much longer. There's other people here that do data, that do leak quantification. You go to some of these pads and they're super leaky. But we found that once you give the customer the tools to fix those leaks, they go and do it and they fix it. And we can bring those levels down to where they're quite manageable, because, as I said, 2 standard cubic feet per minute at 100 pounds is a very manageable supply of air. Your local dentists will use more than that. So if we look at some case studies, Total have gone on the record as we're their key supplier. We were able to use quotes from them, which we do. We're very proud to be a partner with them. They have converted a large portion of their assets down in the Dallas-Fort Worth area to pneumatic air from pneumatic methane. They've been able to offset, north of 7,000 tons of methane a year. They have hundreds of these working. It's been really a good experience for them. Let's look a little bit past pneumatic air, and let's look at some of the other verticals within the industry. This is a vapor recovery tank. We don't have a commercial product yet that we're launching in this space, but it is something we're definitely evaluating and testing. And it's important that this forum would be aware that the same rules apply. You have raw, untreated, dirty methane. That's a liability. It really, truly is a liability, and it's becoming a liability. And so what do we do with this? And the idea behind our technology is, can we take some portion of this liability and convert it into revenue, convert it into some sort of margin tool. And so in this case, we can do a number of things, such as compress pneumatic air or do gas recompression. And so in this specific application, we're pulling the less than perfect. You can look here at the values of the natural gas. We're talking about very low pressures, ounces. These tanks are not designed to be pressurized, so there's hardly any pressure behind the gas. Essentially, it's just enough pressure to make it to leak, but you can't really put it in a pipeline. You can't transport it. Low levels of methane content. the statement, and I really like this statement, these are leaks which are too large to ignore, but too small to have a really good solution for. And that's what we're trying to do. We're trying to address those leaks which are too small to ignore. And we have a small solution, but small solutions, sometimes small is good. And so you have these streams of methane, which are venting that are 55 to 60, 65% CH4 content. Not many technologies out there can convert it into anything useful. High levels of humidity. You can even see in this picture, what you see there is the condensing, water vapor that's mixed in with the methane. High levels of CO2. There's H2S there as well. So it's really corrosive and nasty stuff. And we've just been venting it to the environment. So what we'd look to do is we take some portion of that vented gas. We turn it into electricity, and then we do something useful so as to prevent the rest of that gas from just being emitted. Landfills, the same thing. So we have some applications within landfills. These are closed landfills. These are old landfills. These are landfills that aren't connected to the natural gas network. They don't have sweetening facilities to convert the landfill gas into renewable natural gas. What do you do with it, right? At best, it's to flare it. And that's really been the challenge, at best to flare it. So just getting flares on some of these landfills has been a challenge and a half for local regulators. In most cases, it's just vented to the environment. So how do we provide a solution that can deal with these leaks, which are, frankly, too large to ignore? From agriculture, we've done some projects within the agricultural waste sector, converting animal manure, as well as in some cases food waste, into biogas, which we then convert into electricity, which then that electricity can be used to benefit a variety of different things, whatever within that agricultural sector. So each one of these are very different sectors, but they all have a common theme. We're taking unrefined, untreated, high liability gas, a gas that really, really no one else can use. And we're converting into reliable, continuous electricity, which we can use to mitigate the remainder of whatever that liability is. So the key takeaways is having a remote power generating platform that provides methane mitigating solutions really is key to resolving the distributed methane challenge. Our technologies aren't really fit for centralized methane leaks, but they are very fit for decentralized methane leaks, which the natural gas industry is just a sector which is, historically and known for being not only distributed, but remote and off-grid. So that's it. That's what I have. I'm about 30 minutes in. I wanted to leave some minutes for you guys to interact with the data. I'm happy to share from my experience. And I know some of my people from my team are on the call as well, and they'd be happy to jump in and answer some questions.